Hi, I'm Chris Moore with HVAC Pro Blog, and this week I'm excited to present a webinar that was recorded for my Patreon members 1 year ago on quality installation, specifically how to measure airflow. Without further ado, here's the training. So just to let you know, we're going to cover what is authorized for measuring airflow in ACCA's quality installation specification. If you're not familiar with this and you're a technician, there's a great workbook available that's on ACCA's website. If you go to ACCA.org, it's about $90 if you're not a member, and they'll ship it to you in a week or two. It's all of the information you need to learn how to use your tools to get within the specification required versus design airflow when you set the system up. So the first one we're actually going to walk through is my favorite. It's static pressure. Using a static pressure probe with the manufacturer's blower data in order to identify what the volume of air is. This is probably the least expensive, most repeatable way to get the same answer every time. There are other ways to measure airflow if you're talking about heating and air conditioning systems. The next least expensive way is actually just measuring the temperature rise on a fossil fuel appliance. If you were to clock the meter and you know what the output or net BTUs per hour is, you can do the math and find out what the volume of air is. There are plenty of other tools out there in order to measure airflow as well, cubic feet per minute. And we're going to cover the Trueflow Plate made by the Energy Conservatory, which is one of my personal favorites because it's like many static pressure measurements. Then I'm going to talk about doing a Duct Traverse. This is authorized by ACCA, but unfortunately it's not very repeatable and it's really hard to get accurate measurements in residential applications. But I'm going to tell you, if you do have the ability, how to do that. And then of course, how to use a duct blaster and pressure match to measure volume of air. So those are the 5 methods we're going to cover today that are approved for measuring CFM in residential systems as part of ACCA's QI spec. When you're setting up airflow, you really need to look at what the design of the system was. And when you're designing airflow, typically on an air conditioning system, in the Northeast particularly, we have somewhere between 300 and 400 CFM per ton. But if you're in a drier climate, it might be more like 450 to 500 CFM per ton. When you're using a fossil fuel burning appliance, you're going to want to pick a number that's right in the middle of your temperature rise. Then, after the system is set up and operating, you need to measure the unit at steady state, and it needs to be within 85% to 115% of your design CFM airflow. In this first example, I'm going to walk through how to measure static pressure and how to use a blower chart in order to find out what the volume of air is. If you're not familiar with static pressure, let me give you a quick rundown. Static pressure measures the restriction of the duct system. The higher the restriction, the lower volume of air there typically is, particularly with a PSC or permanent split capacitor style motor. If you have an ECM motor, what's going to happen is that motor is going to ramp up to try to deliver the same volume of air, and it's going to use more electricity as the static pressure goes up. Now, restriction in a residential duct system is actually measured in either pascals, which is the metric version, it's a more exact number, or inches of water column. And believe it or not, this is actually where this measurement came from. The pressure in the ductwork would push down water in a U-tube manometer or an incline manometer, and the number of inches would then read out inches of water column, right? The key conversion here, if you're using inches of water gauge, because that's what we use now with electronic gauges, is that 25 pascals equals 1/10 of an inch of water gauge, or water column. I'm going to be consistent through the rest of the presentation here, and we're going to stick to water column. Now, when you measure total external static pressure, that is the supply plus the return external to the box that's shipped with the motor. So you have to measure in the right spot. There is mechanical gauges still available and very accurate. It's called a magnehelic. They can measure down to 1/100th of an inch of water column. I used to have one. It's definitely a great backup in your van, but for a lower cost, you can buy a very nice manometer or dual input manometer that reads out pascals, because if it reads pascals, it'll read to 1/100th of an inch of water column, which is more like what we need to get to when we're measuring residential duct systems. Of course, in order to do this, you're going to need a static pressure probe, and there is a difference between a static pressure probe and a pitot tube. A pitot tube is going to measure velocity and static to give you total pressure, A static pressure probe actually has the tip blanked off, so it's not going to measure the velocity of the air, it's just going to measure the pressure on the ductwork. When you use this static pressure probe, you're going to want to point the point of the pressure tip into the airstream in the supply. That way the holes are facing the ductwork, not the airstream, so we measure static pressure, not velocity pressure. Now, when we're working on a air handler, like let's say for a heat pump or an air conditioner, it's really simple because the blower is shipped in the same box that comes with the A-coil. So since it's all in one box, if you don't change the filter that ships with the system, which let's be honest, most people do, but it's probably like a MERV 1 or 2 rock catcher, we'll call it, you can stick that static pressure probe into the return duct and then of course onto the supply duct right after that blower, and you're going to be able to add the two numbers together to get your total external static pressure. Now remember, in the return side, it's going to be a negative number. When you have a negative number, when you talk about static pressure, if you're familiar with elementary math, you can think of this as an absolute number. You ignore the negative sign. You add the two together and you get your total external static pressure. So as an example, if I measured negative 0.25 in the return duct and positive 0.25 in the supply duct, the total external static pressure of that air handler would be 0.50 inches of water column. This is a little tougher when we talk about a furnace with an AC add-on. So as an example, with a furnace with an AC add-on, you need to measure prior to the A-coil on top of that furnace because that is not shipped in the box with the blower. Now me personally, I would turn the system off, take the high limit switch out, put a piece of tape over it and stick the probe through there because it's prior to the A-coil and typically near the heat exchanger. So you're able to pick up all of that external static pressure without overestimating what it is actually in the system in the supply. If you replace that air filter on the return duct, you also need to measure in the blower section after the filter because that was not shipped in the blower section with the unit. When you add that, let's say MERV 11 or MERV 8 4 or 5 inch plated filter, you're going to want to include the pressure drop of that filter in your total external static pressure calculation. And what you're going to find most of the time, an A-coil add-on on top of a furnace with a really high-end air filter is going to have a higher total external static pressure than, let's say, a heat pump air handler, because all of the heat pump air handler is shipped in one box. In this last example with the furnace and the A-coil, you're going to want to measure in location numbers 2 and 3 if you have an A-coil and a different filter that's upgraded to the system. Now don't forget, a lot of these high efficiency furnaces and air handlers typically have ramping options in order to get this efficiency, right? So you're gonna have to make sure you're running the system at steady state, which typically takes at least 10 minutes of runtime to get it all the way up to 100% capacity for volume of air. If you were to start this measurement and you're not at 100% capacity, you could now see that you're gonna get varying degrees of accuracy and it's gonna change as you're making the measurements. So make sure you're all the way up to 100%. Now you can do this by waiting the runtime, or you could just jump out the system or change the dip switches in order to get it to run at your full setting right away. Just make sure you don't forget to switch it back when you're done. So in this example, I have a heat pump air handler. And since I used the rock catcher filter that came with it, I measured in the return duct close to the air handler, and I actually on my manometer measured negative 0.19 inches of water gauge, right? Or water column. Of course, in the supply duct, you can see I measured 0.21 inches of water gauge. When I add the two numbers together, we actually have 0.4 inches of water column. Now, in my design, when I did my manual decalculations, I designed this system on medium speed because I had a 2.5 ton air handler. That 2.5 ton fan speed, in order to get above the 1000 CFM I was targeting in my design, the closest setting I had was at 0.5 inches of water column, and that's what I started my design around. Now, when I measured the system, it didn't measure 0.5 inches of water column. I need to measure and make sure I'm within 15% plus or minus from what my design was. So my design was at 0.5 medium speed, which is 1012 CFM. But when I measured total external static pressure, it measured medium speed 0.4, which is actually 1064 CFM. Fortunately for me, I know that's within 5% of my airflow, right? So this is gonna pass quality installation and setup for, let's say, Energy Star homes. And I know on my end, the system is set up the way it was designed. So now if I know I have the right airflow and I sealed all my ductwork right, I can get the air to where it needs to go by balancing the system. Now there's a little bit more math involved when we're just measuring temperature rise on a fossil fuel furnace. Remember, our design is what we're going to use in order to set the airflow, and then when the system's installed, we set the right speed, we measure static pressure, and we verify that the airflow is right with that static pressure probe. With a furnace and you're using temperature rise, instead of measuring static pressure, we're going to measure temperature in the right spots in the return of the supply. And then do this math in order to verify that we're within 15% of the airflow that the system was designed for. So if this furnace, let's say I had the same blower chart, had an output of 63,000 BTUs, and the manufacturer's temperature rise stated it should be within 45 to 75, you're going to want to pick a number right in the middle. This gives you enough leeway, plus or minus, to maintain the manufacturer's specification if everything's not perfect with the ductwork, or you need to turn the fan speed up or down in order to get air to where it needs to go, right? So you can see I did the same thing with this furnace. We designed it around 0.5 inches of water column, medium speed and heating. So you can see that's 1012 CFM, because when I did the math, my design was around 972. So I can't turn this down to medium low. Medium low would only give me 800 CFM or so. I can't turn it up to high because that's 1120 something CFM. I need to put it on medium in order to get as close to that temperature rise right in the middle where it runs the most efficient and gives me enough room for modifications when needed or if needed. So in this example here, I had a horizontal furnace with an A coil. My output stayed the same. Now, in this example, you shouldn't just use the net output because we don't know if the gas pressure was set up perfectly or there's an altitude correction factor, right? You actually should go clock the gas meter in order to get this number on the top side of the equation. But for class and example purposes, I'm just going to use the net output that's published for that furnace. I'm going to divide that by the constant of 1.08 for air. You're going to multiply that by any altitude correction factor. And if you're below, let's say, 1,100 feet, then you're not going to need an altitude correction factor. If you do, there's a great chart in that technician's workbook or guide for quality installation that I mentioned at the beginning of the presentation. And then what our actual delta T was when we measured it on this furnace. In the return, I measured 69.2 degrees Fahrenheit. Of course, in the supply, I measured 119.2 degrees Fahrenheit. When we minus the 2, we end up with a clean 50 degrees. So when I do this math, of course, I'm going to do the bottom side of the equation first, then divide 63,000 by that number, and we end up with 1,167 CFM. Of course, I need to make sure that that volume of air is within 15% of what my design is. Remember, the design was 972 CFM. We are within 100 CFM, which we know is about 10%, so we're good on this one too. So those first two methods I talked about were the least expensive and fairly repeatable. I would say static pressure is a lot more accurate and repeatable than temperature rise. This next method, if you have a central return or a return grill or filter that's close to the system, I would say is the most repeatable, no matter who is sliding the Trueflow Plate into the system. The Trueflow Plate actually comes in two different sizes, and they give you blanks to make up different size filters for filter racks. And you can see in this first picture, sliding it in at the unit will include any sort of duct leakage, so you'll get the actual volume of air going across that A coil. Before you use this tool, you should measure the static pressure in the supply duct first, so you know how the system runs without the tool in and with the filter, because it could be more restrictive or less restrictive than the filter you're using. Then you would take the filter out of the filter rack, slide this tool in with the holes of that bar that snakes through the middle of it. Those holes should be facing into the airstream, and there's actually stickers. Stickers are facing into the airstream, and it tells you on the sticker. You would hook this up to a dual input manometer, read total pressure, and convert that on the chart. Or you can use the manometer that comes with it, or you can purchase with it from the Energy Conservatory, and that will actually have the chart built in, so it literally will read out cubic feet per minute. It's a really neat tool. Unfortunately, if you're measuring this at a filter grill, it may not include all of the duct leakage back to the system. And if you have more than one filter grill, because you have multiple returns, not a good idea to measure this at that grill. You should measure it at the unit, which unfortunately for some of you technicians means getting up into the attic. Now, probably the least repeatable way in order to measure volume of air is using an anemometer and doing a traverse of the ducts. The most popular anemometers that are used out in the field today are either hot wire anemometers or mini vane anemometers. Now, you could also use a pitot tube, and you're gonna probably wanna do that if you have large commercial ducts, let's say 60 inches or longer, because you're not gonna be able to get an anemometer into the ductwork, into the airstream that distance without having multiple readings on both sides. So using a pitot tube for very large ducts is probably ideal. I'm gonna stick with anemometers in this particular presentation just because it's the most likely to use on residential applications. So what you're actually going to do with this anemometer is measure velocity. You're gonna measure feet per minute, and then you're gonna actually have to convert that to cubic feet per minute. There are some practical problems in doing a duct traverse with residential systems. And I'm gonna show you some pictures and some diagrams and a lot of math in order to do this if you have this tool. The number one thing I need you to know is you need to measure in the right location. You need to be 8 duct diameters away from the fan in a straight run, because otherwise there's gonna be a lot of turbulence and it's gonna mess up your reading. So in this example, if I have 8 by something trunk, let's say 8 by 32, we need to be 8 inches times 8 diameters away from the fan, which is over 5 feet away. So I gotta tell you right now, if you're gonna try to do this before any takeoff, because guess what? When you have a takeoff, you're gonna measure less air, right? And you're trying to measure the total volume of air in the system, it's probably not gonna happen in a residential system. But if you do happen to have this situation and you can, great. I think this is probably more for commercial ducts though. Don't forget, you also need to be 2 duct diameters away from any turn. So in this example, 8 inches, because that's the height of your duct, the diameter of your duct, times 2 is 16 inches before any turn because of turbulence. So as you can see, it's gonna be really hard to find a location, but let's say you did. I'll walk you through it here. So if your ductwork is straight enough, the traverse method could probably still give you false results, because if I stick that probe in and I turn my wrist slightly this time, I'm gonna get a different number, all right? You have to be very careful to make sure you hold the probe in the most perpendicular position all the way through. Also, when you're making these holes in the duct, there's a few things you need to make sure you know. If your square inches of the ductwork is 28 square inches or more, then you're gonna have to make at least 16 measurements in order to get a good average. This means if your duct is 5 inches round or larger, you're making at least 16 measurements. That's a lot. It's a lot of holes, it's a lot of measurements, and I'm gonna show you how to do it here. Don't forget that the first hole needs to be at least 2 inches away from the edge of the sheet metal. And that's because of the way the air travels through the ductwork. I'm not gonna get into Venturi effect and all that stuff. Just wanna make sure you know the first hole has to be at least 2 inches off the edge. In this example, let's say I have 8 by 32 trunk like I was talking about before. I need to be 2 inches away from the edge of that 32 inches of duct on both sides. And I need to make sure I'm gonna be able to take 16 measurements here, right? So I'm gonna take a cross section of this duct and I'm gonna evenly divide the area that's available to find out where to make these holes. So if I take 2 inches off of each side, I'm left with 28. And if I wanna take 16 measurements, it's probably easiest to do 5 by 4 or 4 by 4, right? To do at least 16 measurements. So I'm gonna divide the remaining 28 inches by 4 holes to find out that I need 7 inches between each hole, all right? So you can see 2 inches off each edge, 7 inches in between each hole. I can actually get 5 total measurements there. Now, doing that same process for the 8 inches in height, obviously your holes are gonna be a lot closer. They're not gonna be as evenly spaced as this picture, this diagram, but you get the idea. Now, we're gonna get feet per minute measurement at each and every one of these locations. Then we're gonna add up all the measurements, divide it by the number of measurements we took to get the average. We're gonna take the average feet per minute and multiply it by the cubic feet of the ductwork to get cubic feet per minute. Now, to get cubic feet per ductwork, there's some more math involved. We need to take the square inches of the duct system, divide it by a square foot, which is 144, to get cubic feet. So in this example, 8 inches by 32 inches is 256 inches. We divide that by 144 inches, and we end up with 1.8 cubic feet. In this example, if my average feet per minute ended up being 620, I would multiply 620 by 1.8 cubic feet to get 1,116 CFM. It's as easy as that. A little tougher with round duct traverse. If you're gonna do a traverse of a round duct, remember you need to find the area first. That's gonna be pi times the radius squared. The radius is half the diameter. So if we had that 5-inch duct I was talking about, the radius would be 2.5 inches. And of course, pi is 3.14. So you're gonna square the radius, times it by 3.14 to get area, divide area in inches by 144 to get cubic feet, multiply that by the average feet per minute that you get when you do these readings, and you end up with cubic feet per minute. Whew, it's a mouthful. Now, the last method I'm going to talk about is probably pretty simple if you're already having your duct blaster connected because you're doing a duct test. Let's say the inspector in your town is requiring you duct test and make sure you meet the requirement in the International Mechanical Code and the ACCA for duct testing. If you already have it connected to the blower section of your furnace or air handler, you could actually seal off the return and match the static pressure when the system actually is operating, right? With the duct blaster, so all the air comes through the duct blaster. You can turn that fan speed up on the duct blaster, match what the static pressure is in the supply when it's normally operating, and see that full volume of air coming through the duct blaster. This works really good when you're like 1200 CFM or less, but when you're over that, there's still some math that has to be done because we can only get so much volume of air through that, it's like a 10-inch or 12-inch duct there. So really important, if you do this, you seal the return off well. Most people would put that mask over the filter and slide the filter back in so it's totally sealed off at the furnace or air handler. So all of the air you're pressurizing with is going into the supply. If it's leaking by in the return, you're gonna get a much higher reading of volume of air in order to get the pressure up in the supply than you really will operate without that duct blaster connected. All right, so that's the 5 methods of measuring airflow for the ACCA QI spec. Remember, when you're setting up an air conditioner, you're gonna wanna make sure you set the airflow first before you adjust the refrigerant charge for obvious reasons, because if you adjust the airflow again, you're gonna then adjust the refrigerant charge again. And make sure the airflow matches the condenser size. Very, very important. Not the coil size. There are a lot of rebate eligible systems going in across the United States where the A coil needs more surface area to pick up more heat to make it more efficient, so it might be a half a ton or a ton larger than the condenser. Make sure you match the airflow to the compressor or condenser size. Also, with a gas furnace, you're going to want to make sure you adjust the gas pressure, the manifold pressure first before you measure airflow. For obvious reasons, you're gonna have to clock that gas meter to get the actual gas output in order to get the math correct if you're measuring temperature rise. Of course, you're not gonna have to worry about that if you're using a static pressure probe or a Trueflow plate. Don't forget to adjust the density of air. There's some great charts in the QI spec. Also, if you need to adjust for altitude correction, that is also in there. Don't forget, altitude correction also impacts how many BTUs per thermal gas, right? When you're clocking that gas meter. All right, so we talked about static pressure, temperature rise, how to use a Trueflow plate, duct traverse with an anemometer, and even duct blaster pressure matching. What did you think of the training? Have you not used any of these in your testing and diagnosis? I'd love to hear your comments below. Don't forget, if you like these trainings and you want to get them 1 year in advance, head over to my Patreon page where you can get access for the last 2 years worth for just $8 a month. Thanks for joining me this week at HVAC Pro Blog, where we provide advice for residential system design, quality installation, and system diagnosis. I'll see you soon.